Hello everyone. Today I will talk about this interesting JAMIA paper about spatial-temporal attention network for pandemic prediction using real-world evidence data. And this is a paper published on JAMIA, this very recent paper, and it's a joint work by Junyi Gao and Rexis Sharma, Cheng Tian, and Lucas Glass, and Jeffrey Spatter, Justin Rumber, myself, and Danny Cashel. And it's a truly collaboration between academia institution and industry. It's a joint work from IQVIA, Georgia Tech, Temple University, and University of Illinois. So let's start it. So this COVID pandemics definitely changed everybody's life, and as of today, we can see the cumulative COVID cases has reached 115 million globally, and cumulative deaths has reached 2.5 million. And this is a curve over time, and this is information we got from this particular website from Johns Hopkins University. So if you want to build a predictive model and that can do early prediction of this pandemic outbreak, and that can help policymakers to design better policy and also reduce the costs associated. So what are the challenges associated with pandemic prediction? There's quite a few. The first one is about how to utilize this spatial information to do better predictions. And most of the traditional epidemiology models actually build separate models for different locations. For example, they can build a model for Chicago, and a separate model for New York, and another model for Seattle, and so on. So it doesn't incorporate spatial proximity. Actually, intuitively speaking, spatial proximity really matters. And you can imagine if nearby location have a lot of COVID cases, and it may affect your location as well because you're close to that region. And not only spatial proximity matters, we can also consider other type of interaction. For example, population movements, demographic similarity, right? Maybe two cities may have a similar pandemic patterns, like Chicago and New York may have a similar behaviors, and two rural county may have a similar behaviors. So that's the first challenge. The second challenge is about how do we incorporate more reliable data. And traditional models heavily rely on the case report data. So we all know those are can be underreported, especially when the pandemic is just happening. A lot of those reporting data may be unreliable, and there could be a latency of those reports. And however, there are other type of data may be more reliable, such as the real-world evidence data, like medical claims data. They're widely available and could be very comprehensive and more accurate. So that's the second challenge. Can we incorporate other type of data to make a better prediction? And the third one is, how do we choose the right models? Right? And most of the pandemic prediction depends on those epidemiology models, such as SIR and SEIR. And this stands for susceptible, exposed, infectious, and recovery. So that's the SEIR model. It has a lot of benefit. For one thing, it has a very few parameters. So if you don't have a lot of data, you can fit this type of epidemiological models very well. And however, this type of model, because it only have very few parameters, is unable to capture very complex short-term patterns, such as superinfections, time variance, infectivities, and so on. Right? Those very subtle and complex patterns would not be captured by this type of model. On the other hand, there are data-driven models, such as deep learning-based models using such as LSTM, GRU. They are good to model sequential data. However, they only can predict known data patterns, and usually for short-term predictions. And so maybe we can combine them, right? That's where this work comes in. They proposed this model called STEM that incorporate both the epidemiological model as the regularization and also leveraging deep learning models so that we can build accurate models by leveraging large amount of data. And in terms of the model itself, it has a few steps. First, it constructs this graph, location-based graph based on location similarity, some static feature about those locations, and also the dynamic features at those locations over time. And then they fed such graph into a graph neural network called graph attention network, or GAT model, and to learn a representation for each location. Then those representation will be the input for a gated recurrent unit model, or this RNN-based model, to make prediction for new cases and recovery cases and some epidemiology model parameters. And then they combine two different loss functions, the prediction loss and this SIR constraints, and that's the kind of the entire model. So let's go through those model, different components of the model in more details. For the graph construction, so they construct this this graph or attributed graph, and that represent this both static feature and dynamic feature. A static feature include, so first of all, each node on this graph corresponding to a location. So there could be a county level graph or state level graph, right? Each node will correspond to a county or state. Then for each node, it has some static feature, the location of the geolocation of that node, and the population size, and the density of that location. Right? Then there are some dynamic feature. Those are features can change over time, including number of COVID-related diagnoses, and the number of hospitalization at that location, and the number of COVID cases. So those are the dynamic features, right? Those are all the features associated with each location. Then they construct this edge, right? So this edge weight is proportional to the population size of this two location, right? Location I and J, as well as the distance, right? So inverse to the distance. And then alpha, beta, and gamma, those are hyperparameters will be set by the algorithm. So that's the graph construction. And the second step is to kind of build this neural network. It has the two layers. One is this graph attention network layer. The purpose of this GAT model is to extract spatial relationships among different locations. And so the input feature, which are those features we have described, both static and dynamic features, and then it passes through this graph neural network and to GAT to get embeddings for each location. Then those embeddings will be passed through another neural network module called gated recurrent unit, or GRU, to extract the temporal patterns. And finally, the output of the neural networks are those predicted cases, delta I, and the predicted recovered cases, delta R. And so these are the two output that we really cares about. Then in addition, we also have two other output, gamma, beta. Those are disease transmission rate and recovery rate that will be used to add the epidemiological model into this neural network. And next, we can look at the how the loss function is formed. And there are two different parts of loss function. Right? The first one is this prediction loss. That's pretty standard for a regression type of model. And we're essentially measuring the predicted number of infectious cases, right? Number of COVID cases, and subtract the real number of cases at this location at that time. So this is square loss on that. Then similarly for the recovery cases, right? Number of predicted recovered cases, subtract the true recovery cases. And so that's a prediction loss. And then we also have this physical constraint, or this constraint by the SIR model. Once we have the beta and gamma, and those are the model parameter for the SIR model, we can use the SIR differential equation to estimate the number of infected cases and the recovered cases. So those will be the model estimation if we use a SIR model. And that will be used as additional regularization to our prediction. So we want this SIR model predicted cases to be similar to what the neural network actually predicted. And so that's kind of bringing additional regularization to the overall model. But of course, this is only done at the training phase. At the test phase or inference time, we only use the neural network model to make the prediction. And this SIR model will not be used in the inference time. So now let's look at the experiment. In the dataset, we're using a dataset that coming from the Johns Hopkins University and the COVID Resource Center. And so that's where we got the day-to-day statistics at different locations. And also we use the medical claims data from IQVIA. So there we have close to 500,000 patients across 48 states. And next, some detailed setting. And this work is done earlier last year, mid last year. So we're using March 22nd to May 17th data as the training data. Then we test the performance of the model in the next 20 days, right after May 17th. And we conduct the prediction on 45 states because at that time there's only I think we have a threshold of 1,000 confirmed cases to be considered. I mean, if it's below 1,000, they're not included in this experiment. So we have 45 states and 193 counties, right? They already have over 1,000 cases at each of those locations. And the metric we're using are mean squared errors, mean absolute error, and this concordance correlation coefficients. And in all these cases, MSE and MAE, the lower the better, and this concordance correlation, the higher the better. So let's look at the state level prediction result. And this table shows the performance when we predict 20 days in advance, right? So we want to predict next 20 days, for each of those 20 days, what are the number of infectious cases, new COVID cases at all those locations, and in terms of MSE, MAE, and CCC. So you can see that comparing to this different baseline model, SIR, SEIR, those are epidemiological models, or also compare to some neural network models such as a GRU model. There's two different models specifically designed for COVID data, COLA-GNN and COVID-GNN. And we also have a few variation of our method, STEM, without the physical constraint or without the epidemiological models, and the STEM without the graph neural network, and the full STEM model. So you can see the STEM model performed the best, right? Significantly improve over all this baseline, right? In fact, in terms of best baseline, we're improving over 48% lower in terms of MSE, and for this 20 days prediction. And you can also see the variation of our different STEM model, and this without the graph neural network, the performance actually drops quite a bit. So this location proximity is very important in making a good prediction. And also the epidemiological constraint is also fairly important, not as important as the location proximity, but still it has a significant impact. Adding that, the performance improves. So that's the state level prediction. And we also did this for the county level prediction. I mean, similar observation. You can see that across, compared to all the baselines, we're significantly better. And all these three different variations, the full STEM model significantly outperformed the others. So in terms of the overall improvement, it's over 55% lower MSE for 20 days prediction, and similar performance for 15 days, and a little bit less performance gain when we do a very short-term prediction, right? Five days, for example. So we can see some example prediction plot, right, for 15 days, or I think. And you can see that here the blue curve is the STEM prediction. The red crosses, those are the actual ground truth number of cases each day at California and Massachusetts. You can see that the blue curve is very close to the red crosses. So that means the STEM model performed really well. Comparing to the other two baselines, SIR, SEIR, those baselines predict much worse, especially for this longer term prediction. And we also give you another example for the county level prediction, you can see that for 2 different county, much smaller number of cases, you can still see a big improvement. And in our case, the STEM model performed very accurately. The blue crosses and the red curve, the blue curve and the red crosses are matches very well, and the baseline performed much worse. Okay, so in summary, this paper talked about a spatial-temporal attention network model for pandemic prediction using real-world evidence data. And if you want to try out this model, the code can be downloaded from this link. And thank you very much.